So today we're going to be looking at applicative functors, which is the second step on our journey towards defining and seeing what monads are. But first, as usual, we're going to have a quick review of what we did last time. So what we did last day is we introduced the idea of functors, which generalize the idea of mapping to a larger family of data structures. So here's our old friend, the map function, which you're all familiar with if you've done Haskell. So what map does is it takes a function from A to B, and it takes a list of A's, and then it's going to apply the function all the way across the list to give a list of B's. And it's got a simple recursive definition as we see here. And the observation we made last day is that the idea of mapping is not specific to the list data structure, so working with a list of A to list of B, but actually can be generalized to give the idea of what's called a functor. So down at the bottom of the slide here is the class definition in Haskell for what a functor is. So what this is simply saying is if we have any old parameterized type f, then it's a member of the functor class, provided that it has a function called fmap of this type. And note that we can't call the function map because map is already used for lists. So the generalization to an arbitrary data type is called fmap. And the type of fmap is just a straightforward generalization of the original type of map above. So we take a function from A to B as before, but now we take an f of an A to an f of a B. Okay, and f could be something like list or tree or maybe or so on. So the idea is that mapping is not specific to the list data type, but can be generalized to any other, generally container-like data types. So that's what a functor is. So what we're going to be looking at today is generalizing the idea of mapping further to functions that have more than one argument. And this is going to give us the idea of applicative functors, which is covered in chapter 12.2 of the book. So let's think about generalizing fmap then to functions with more than one argument. So we're going to be generalizing the fmap function. So let's first of all think about what types we might have if we generalize this. And we're going to write a whole hierarchy of different function types down here. So let's write fmap of 0. That's going to be taking a function with 0 arguments. Fmap of 1. Fmap of 2. Fmap of 3. And we'll stop there. So let's try and fill in what we think the type of fmap should have if we generalize it to functions with more than one argument. So let's fill in the easy case first of all. So if a function has one argument, that's just the familiar fmap function, which goes from A to B to f of A to f of B. So it's a function with one argument here, an A, and then we take one data structure, an f of an A, and we give back an f of a B. So that's the case we're already familiar with. So let's think, how then could we define the type of fmap2? So it's going to take a function with two arguments, so it's going to take an A to a B to a C. So the point here is that we're taking a first argument and a second argument, and then we're returning a result. So it's more general than fmap1. And then what we're going to do is we're going to take two data structures. We'll take an FA and an FB, and we'll process those to give an FC. So this is generalizing the idea of mapping to functions with two arguments or two parameters. And then we could play the same game with fmap3. We have an A to B to C to D. So here we have three arguments, A, B, and C, coming in, and one output, D. And then we take three data structures as input. We take an F of an A, we take an F of a B, and we take an F of a C, and out will come an F of D. So we might think, well, what's the degenerate case? Now, what's fmap of 0? And if you think about the pattern here, if you see what's happening, we've got kind of a shrinking triangle here. And we can play the same game in the base case. We can just say we have a function with no arguments, which is just a constant, which is just a single parameter A, and then we'll give back a result of type FA. Okay, so here are our kind of hierarchy of functions which we'd like to think about for generalizing fmap. And you might think, well, what do these things actually do? It's quite clear what fmap1 actually does. I mean, that's just the thing we're familiar with from normal functional programming. We map a function over a data structure. Let's have a simple example to show what fmap2 might do. So if we had an fmap2 defined with the type above, we might be able to do something like, say, fmap, and we might take the addition function, which takes two integers and adds them together to give a single integer. And then we might take two just values. We might take just of 1 and just of 2. And the mapping function would do the obvious thing here. It would unpick the two maybe arguments, and I get the two parameters 1 and 2, and we get back just of 3. So you can see here now what these kind of generalized mapping functions might actually do. So the question now is, how should we achieve this kind of behavior? How should we achieve being able to define mapping functions which take as many number of arguments as we like? Well, one way we could do this is we could declare a new class to handle each case. So for example, we could declare a class of binary functors, say functor2, and this is functors where the parameterized type f takes, not the parameterized type f rather, where the mapping operation takes functions with two parameters. So we could say a functor2 is got to have an fmap2, and fmap2 takes a function with two parameters, a to b to c, so we've got two parameters a and b, and it's going to take an f of a, and an f of b, and an f of c. So we could do this for each of the functor classes which we require, like functor2, functor3, functor5, and so on. But as I'm sure you can imagine, there's a number of problems with this. The first of all is it's quite tedious. I mean, we'd have to define manually functor2, functor3, functor4, and so on. And they all follow a similar pattern. And you can also ask yourself, how many should we actually declare? Should we stop at 3? Should we stop at 5? Should we stop at 100? And whatever number you come up with, somebody's going to come up with an application where they need just one more, and then they need to manually define the functor class. So it's a bit of a problem here. We'd like to consider functors which take functions with more than one argument, but we don't want to have to go to the labor of defining a whole hierarchy of different class and instance declarations to handle this. So fortunately, there's a very nice solution to this, and this is what gives rise, as we'll see, to the notion of an applicative functor. We can actually build any mapping operation we need just in terms of two basic functions. So if we have two basic functions, we can build map2, fmap2, we can build fmap3, fmap100, we can build any of the ones that we want. So here's the two magic functions that we need. We need a simple function called pure, and we'll see later on why it's called pure. And it simply goes from a to f of a. And then we're going to need a funny star operator, and I'll come back to the notation for this in a second. So the funny star operator is going to take an f of an a to b, and then it's going to take an f of an a, and then it's going to give you back an f to b. Okay, and I'm going to call this the kind of funny star operator or the star operator. So why do I need these round brackets round the star operator? And that's because I'm using it here as a prefix operator. I mean, normally when you write something like x times y or x star y, you write the star or the funny star between the arguments. But when you give the type of things like this, you need to put the brackets in here. So that's why the brackets are here. So what's actually going on with this? Well, the way you think of it is the function pure is going to convert a value of type A into a data structure. So it may take a value type A and convert it into a list or a maybe or a tree or something like that. So it's embedding a value into a data structure in a simple way. And then what's the funny star operator doing? Well, it's just a generalized form of function application. You can see that there's basically a function application type hidden in here. Function application takes a function from A to B, an argument of type A, and then gives you a result of type B. And that's exactly what we've got here, except we're taking a data structure which contains functions of type A to B, and then we're taking a data structure which contains arguments of type A, and then we're applying one to the other in the appropriate way, and we're giving back a data structure which has values of type B. So the way we're going to think of the funny star operator is it's a generalized form of function application. Okay. So how do you use these things? Well, a typical use of these two functions has this form. What you typically do is you write pure of some function g, and then the funny star, and then arguments to the function. So we could have 3 arguments here, x, y, and z. Okay, so this is a typical application here. What we're doing is applying pure of a function g to 3 arguments, x, y, and z, using the funny star operator here. And there's a special name for expressions of this form. This is called applicative style. Okay, so if you write things in this form here, let me just highlight that again. If you write things in that form, this is called applicative style. And that's really what we're going to be looking at today. How do you write functional programs in applicative style? And it's called applicative style because it's very similar to normal function application. So if we were just applying a function g to 3 arguments, we would simply write g, x, y, and z. Okay, so that's normal function application style. So what we have above here is exactly the same, except there's something funny going on with functors, because we're not just writing g, x, y, z, we're saying pure g applied to x, applied to y, applied to z, with this funny function application operator. Just a quick comment before I move on. The star operator brackets to the left just like normal function application does. So when I write g of x, y, z down the bottom, that really means this, really brackets to the left. And it's exactly the same up here. When I write pure of g applied to x, y, and z, it's really bracketing to the left. Okay, so that's an important thing to remember. The difference, however, between applicative style and normal function application is that the type of the arguments are more complicated. There's some functor stuff going on. So I claimed that using these two functions, pure and funny star, you can define any mapping operation you like. So let's actually see how that works out in practice. Let's define the first few mapping operations. Let's see how we could define f map of 0. So f map of 0 went from A into f of A. So I can think, well, how do I define this using pure and using the star? Well, this one's very easy because f map of 0 is just pure. Okay, because pure on the previous slide goes from A into f of A. Okay, so if I've got a pure and I've got a funny star, I can always build an f map 0. That's no problem. So let's try the next one now. Let's go on to a new page here. Let's have f map 1. How do we define f map 1? Well, it takes an A to B, and it takes an f of an A, and it gives back an f of a B. So it takes a function from A to B, a data structure that contains A's, and it's going to apply the function to the data structure and give you a data structure that contains B's. So how do I define this? Well, let me just write down the definition, and then I'll explain what's going on. So f map 1 of g, that's the function parameter, and then we take the data structure, and I'm going to use applicative style to define this. So I'm going to write pure of g, and then the funny star, and then the argument x. And I claim that this has the correct type. And it's very easy to check this. So let's have a look at the types of everything. So let's have a look at the type of the argument g. So g goes from A to B. So I can kind of note the type down here. That's an A to B. And the parameter x, that has type f of A. So I can write that one down as well. That's an f of an A. And then I go across to the right-hand side. Well, what happens when I write pure of g? Well, what pure does is it takes an A and gives you back an f of an A. But in this case, the argument is a function g, and that goes from A to B. So what we're actually going to get back here is we're going to get back f of A arrow B. So that's simply applying pure to the function g, which has type A to B. So we get the type f of A to B over here. Then we can think, well, what's the type of x? And that's very easy. It's just given to us on the left-hand side. That's an f of an A. So now we can think what happens when we apply the star operator. So star is going to take the f of A to B and the f of an A, and it's going to give us back let's write this down here, it's going to give us back an f of b. And that's exactly what we want. We want an f of b in the end here. So it's not much of a spectator sport watching somebody kind of track through types, but this is a really important exercise to be able to do this yourself. So if it didn't make sense what I was doing here, kind of write down the definition for yourself and track through all the types and make sure you understand how everything is fitting together and that all the types are correct. That's very important when you're learning about applicative functors. So let's just do one more. Let's have f map of 2. If I wanted to define f map of 2, it's got type a to b to c. It takes a function of 2 arguments, a and b, and then we're going to take an f of an a and an f of a b, and we're going to get back an f of a c. And I can define this completely straightforwardly if I wish to using applicative style. I take my function g, I take my 2 data structures x and y, and I'm going to simply use applicative style here. I'm going to write pure of g applied to x applied to y. Okay, and I'm not going to go through the details here, but I do suggest that you check that this expression on the right hand side here has the right type. Okay, and check through all the types. And the trick here that you need to remember is that the star brackets to the left, so you probably want to put some brackets in here, and then you won't go wrong when you're working out the types. So what we've seen now is how using the simple pure and the funny star operator, which is the generalized function composition, that gives us the power to build any mapping operator that we like that takes functions with any number of parameters. So this leads us now to the idea of applicative functors. So an applicative functor is simply a functor that supports the pure and the star operator. And usually we call these applicatives for short. So let me give you the formal definition for this now. So we have a class declaration, and we have the requirement that we already have a functor, because in order to be an applicative, you must be a functor already. And we're going to declare the applicative class, applicative, and all you have to do is provide the pure function, which embeds a value into a data structure. And you're going to need the funny function application star, and it's going to take an f of an a to b, so a data structure that contains functions, and then it's going to take a data structure that contains arguments, and then it's going to give you back a data structure that contains results. And again, this is exactly the definition for the applicative class that you will find in the Haskell library. So it's anything that's a functor that supports a pure and a funny function application, and that's basically it. So what we're going to do for the rest of today is look at some examples of applicative functors and see what we can do with them. So the first one we're going to look at is the maybe applicative. So let's look at maybe. So we already made maybe into a functor in the last class, so all we need to do to make it into an applicative is define the pure and the star operator. And again, just like with functors, we're going to let types guide us here. So we're making an instance declaration, and we're saying that we have an applicative for the maybe type, or the parameterized type maybe, and we'll write down the types of pure and the types of apply. And again, we need to write these in comments because Haskell doesn't let us write types in instance declarations. So pure goes from a to maybe a, and you think, well, how do you go from an a into a maybe a? Well, this is very easy. There's only one way to do this. Pure of x is, or one sensible way to do this, pure of x is just of x. So you can embed the value trivially into the data structure just by tagging it with just. Then we can think, well, what do we do for the function application or the generalized function application? Well, let's write down the type because that will help us. So we take a maybe of a function, and then we take a maybe of an argument, and we're going to get back a maybe of a result. Okay, so we take a maybe of a function, we take a maybe of an argument, and we get back a maybe of a result. So let's write down the skeleton for this first, as usual. So the first thing could either be nothing, and then we have a star, and let me call the argument mx to remember that it's a maybe. And then we have just of a function, and we have the star, and we have the argument. And then we just need to play the same games with type, the same game with types that we played last time. So what we have here is we have an argument of type maybe A, and what we want to write over here is a result of type maybe B. But in this base case here, we don't have a function over here. We've got absolutely nothing, or literally nothing. So we think, what can we actually write on the right-hand side? Well, the only sensible thing, or the only thing we could really write over here is actually nothing. Okay, so the function application symbol, star here, if you give it a function which has failed, and you give it an argument, then there's nothing to do. You're going to simply fail as well. Okay, so that's the first of the cases. In the second case, we need to think, what have we got? Well, if we think, what is the type of the function g? Well, g is going to be an a to b. And then we can think, well, what's the type of mx? Well, that's given to us in the type above. For the star operator, that's going to be a maybe a. And what we want over here is we want something of type maybe b. So if you've got a function from a to b, and you've got a maybe a, how do you get a maybe b? Well, that's just mapping. And so we can use the f map for the maybe applicative, and that's okay to use because in order to be applicative, you must be a functor as well. So we do have an f map. So we can simply write over here f map g to mx, and that will give us something of the right type. And in fact, this is the right definition here. So again, this is a pretty simple example, but if it doesn't make sense, reconstruct it with on your own. And that's the kind of general advice for everything I'm going to be teaching you in this course. A lot of it is a kind of game with types, kind of writing down a type and trying to figure out what's the right thing to do. And always in this course, if you just write down the obvious definition, it will work. So if this doesn't make sense, reconstruct it for yourself, and it's also explained in the book as well. So let's have a couple of examples now of actually using this in practice. So let's have some examples. So this is all built into GHC. So the functor class, the applicative class, the instance for maybe and lists and so on. These are all built in, so you can just start up GHC and use them. Let's try an example. Let's try applying pure of +1 to just 1. Okay, so here we're taking the increment function, which has one argument, and then we're giving it an argument that may fail, but here it's actually succeeded. And of course, what you're going to get back here is exactly what you'd expect. You're going to get back just of 2. So all the machinery here is going to do is the pure machinery and the star machinery is just going to unpick everything and apply that function +1 to the one inside the just and gives us back just 2. So let's have a more interesting example now. Let's apply pure of plus. So plus is a function which takes 2 integers and gives you back a single integer. And then we're going to apply it here with the applicative machinery to 2 arguments. So the first one is just of 1, and the second one is just of 2. And this is going to do exactly what you would expect. It's going to apply the plus function to the 1 and the 2, which are both successful results because they're tagged with just, and we'll get a successful result again. We're going to get back just of 3. So what you start to see here now is that the applicative machinery with the maybe functor is giving you a simple way of programming with things that can fail. In this case, we're applying a function, a pure function, plus, to 2 arguments, and both of them have succeeded, and we get the result back just of 3. So we could try what happens with an argument that fails. So let's try the same example. Let's apply the pure function plus to nothing. So that has failed. And let's leave the second argument alone. And not surprisingly, we have a function here which takes 2 integers and gives you back an integer. We have an integer over here that's successful, but this parameter here has failed. And not surprisingly, if you track through all the machinery, you'll find that this is going to give you back failure. You get back nothing. And there's a couple of important points to make here. The first one is it's really good to try expanding out these examples to see how they work. So for example, you might want to take the first example here and just expand out the definition of pure, expand out the definition of the generalized star operator, and check for yourself how you actually get the result just 2. And the second point kind of generalizes from all of this, and it's what applicative style for maybe is really about. So the kind of the slogan here is that applicative style for maybe supports a form of exceptional programming where we can apply pure functions to arguments that may fail. And we've seen a couple of examples of this here. Here we're applying the pure function plus to 2 arguments which have succeeded, and we get a result which has succeeded. Here we're applying the pure function plus to an argument which has failed and an argument which has succeeded, and what we get is the failure propagated, because fundamentally the plus operator is a pure function. It takes 2 integers and gives you an integer. If you don't have 2 integers, there's nothing you can do, so you get back the value nothing. Okay, so an important point here, applicative style for maybe supports a form of programming with exceptions, or exceptional programming, where we can apply pure functions to arguments that may fail. So let's look at one more example now for today, and the example we're going to look at is lists. So let's look at lists. So lists are already functorial. That's just the familiar mapping operation which we started with last time. And we're going to make a simple instance declaration here. We're going to say that lists are going to be applicative. And remember, the parameterized type for lists with no parameter is just the open square bracket, close bracket. It's not the empty list here, that's the parameterized type for lists. And we can write down the type for pure. And what pure is going to do is take an A and embed it into a data structure, which in this case is a list. So what pure is going to do is very simple. The natural thing to do is just to put the thing trivially into a list. So you see again, pure is going to be a basic operation which trivially embeds a value into a data structure. So in this case we take x and we make it into the trivial little list which just has x on its own. Then we need to think about the star operator. So let's write down its type again. So the generalized star, the funny star, it takes a list of functions this time, which is a bit of a strange idea, a list of arguments, and we're going to get back a list of results. So how do we put all this stuff together? Well, we could do this with a list comprehension. We take a list of functions, g's, and we're going to apply it to list of arguments, x's. And it turns out that an appropriate way to do this is just to consider all combinations. We're going to apply all functions to all arguments, and then we'll get all possible results. So we're going to take all possible results, g of x, such that g is a function from the input list g's, and x is an argument from the input list x's. So what we're doing is taking all possible functions, all possible arguments, and applying one to the other in all possible ways. Okay, so this is, again, kind of type-directed programming. We define the definition for pure, based purely on the type, very straightforward, and we define the definition for the star operator just by making the obvious definition based on the type. So let's see how we could actually use this in practice. Let's have some examples and then think, what does this actually all mean? Well, what we've got here is we could apply pure of +1 to 1, 2, 3. Okay, so we're applying the increment function +1 to a list with 1, 2, 3 in it. And you can guess what this is going to do. It's just going to behave simply like mapping. Okay, this is just another way of doing mapping. So we're going to get 2, 3, and 4. Okay, so that's not very interesting. We could have just written map or fmap to do this, so not particularly interesting. So let's try applying a function with more than one parameter. So let's take pure of plus. So again, plus takes 2 integers and adds them together. And here we're going to apply it to a list with the number 1 in it and a list with the number 2 in it. And you think, well, what's this actually going to do? Well, it's simply going to take the plus operator and apply it to everything in this list, of which there's only 1, and everything in this list, of which there's only 1 as well. And then we're just going to get back a simple list with 3. Okay, so again, not particularly interesting. I could have just written 1 plus 2 in a list to get this behavior. But you see the power of this notation when you start to consider longer lists. So let me write pure of star. So star here is just a normal multiplication operator. It takes two integers and multiplies them together. And then I'm going to apply that using the funny star operator to two lists which have more than one element in them. Okay, so what I'm doing here is I'm applying multiplication, which is a pure function, to the list 1, 2 and the list 3, 4. And if you type this into GHC or you work through the details yourself, what you'll find is that this multiplies one value from the first list with another value from the second list in all possible ways. So we could multiply the 1 and the 3, or the 1 and the 4, or the 2 and the 3, and the 2 and the 4. So we're going to get back 4 possible results here. 3, 4, 6, 8. Okay, so that's what we're getting back here. We're applying a pure function star to a list 1 and 2 and a list 3 and 4, and we get back all possible ways of multiplying one value from the first list with one value from the second list. So if you think about what's actually going on here, just like we had a slogan for the maybe type, so we can have a similar slogan for the list applicative. And the idea is that the applicative style for lists supports a form of non-deterministic programming where we can apply pure functions to multi-valued arguments. And you see that in the last example here. What we're doing is we're applying a pure function, which is star, to a multi-valued argument, 1 and 2, and another multi-valued argument, 3 and 4, and we get back a multi-valued result, 3, 4, 6, and 8. So again, important point, let me just repeat it. Applicative style for lists supports a form of non-deterministic programming where we can apply pure functions to multi-valued arguments. So that's it for today. We've introduced now the idea of applicative functors, which generalize the idea of mapping to functions with more than one parameter. And what we've seen is that if you have the simple pure primitive and the simple generalized function application primitive, the star, that's sufficient to let you build any kind of mapping operation that you like. So that's it for today. See you again next time.